Good afternoon, everyone. Hope you have a great weekend. So let's get started. So for today's lecture, we'll continue to talk about deep learning. And also for the next lecture, so we'll have these four lectures to give you a crash course about deep learning. Okay. So just do a quick recap from last week. So we discussed the fully connected V4 neural networks. We also talk about convolutional neural networks, which are very useful or used a lot in image processing and computer vision. And we specifically talk about some of the component in terms of network optimization, right? How do you specify the loss function? For example, the cross entropy loss, and how you will optimize the network. We can have a training set, and we can specify some of the optimization method. For example, the stochastic gradient descent, right? How it works for the optimization. We also discussed some of the practical issues in training the deep neural networks, right? Specifically, we have to be careful about the model overfitting, right? If you encounter some of the overfitting issue, then the learned model is not going to be generalized well on the test set, which means the performance on the test set will be maybe very bad. Okay, so we mentioned a couple of regularization techniques that can alleviate the overfitting issue. For example, we can using the dropout, right? We can using the weight decay, right? Specifically penalize those large parameter weights in the network. So these are the common techniques. When you also doing some of the projects or implement the neural networks for a specific data set, these are some of the techniques you can consider to stabilize the training of your deep neural networks. We also talk about data augmentation, right? So this is also a very common technique. In practice, for our target application, we may not have a lot of data. So this will also cause overfitting issue because some of the large network is very data hungry, rely on large training data to learn meaningful representation or to combat the overfitting. So data augmentation is a very useful or commonly used technique that you can increase your training data so that somehow also alleviate the overfitting issue. Okay, so here I provide more reference or resources for you to look into, in particular this data augmentation. And I also want to discuss another very common practice used in training deep learning models. So that is the transfer learning. So as we mentioned, right, so the data, the limited data could be very common in a lot of applications, especially in the medical image or medical computing domain, right? So some of the medical images are very scarce because for some of the disease, we may not able to collect a lot of patient data, or maybe for some other reason, right? The patient privacy, we are not able to release a lot of training data to the public. So you end up with a very limited training set, and this will cause issue for training the large deeper neural networks. So typically, this transfer learning, basically you can leverage some of the existing large scale data set, right? So in image processing, computer vision, right? So we have this ImageNet data set, which is a large scale data set that contains a million of even more images for training. And the data set is public available, right? As a matter of fact, there's a lot of deep neural networks have been trained on ImageNet, right? So for example, ResNet, DenseNet, and later, we have some other advanced network like the Vision Transformer, etc., right? So these state-of-the-art deep neural network have been trained using the large-scale ImageNet database. So I think the rational thing we should consider is, can we leverage some of the knowledge right, has been, that is learned from this large scale public available data set, right? So that's the notion of transfer learning. We want to transfer some useful knowledge from these database to the target data set at hand, right? So concretely here, show in this diagram, right? So we have a network, right? So this is the network architecture. We have a simple CNN network, and we have the input data. So let's say this is the ImageNet, right? So this public available large database, and we have a pre-trained model on this ImageNet, right, for image classification. So, and now we have a target data set. We call this B, right? So we have a target input B. Let's maybe make another example. We want to do, X-ray, chest X-ray, right, tumor, detection or classification. Okay, so how can we leverage these pre-trained model for our specific task at hand, right? So there's a notion called transfer learning. Simply put, basically the idea is that we can maybe transfer some of the learned representation from the network layers, right? Maybe the first or initial layers, right? As we discussed in the CNN, right? So different layers, they learn different representations, right? The initial layer or the first couple of layers, they learn the very basic or fundamental information or structures from the image, like edges, corners, or combination of edges, etc. Right? So these information, we can consider they are fundamental information, right, to any images, right? Not just in particular to natural images, but for other other domain images like medical images, those are still like considered fundamental or useful, right? So maybe those feature we can directly use, right, rather retrain it using the data set, right? So we can directly adopt these feature representation here from the pre-trained model, and using them, what we do is we using the target data set to kind of fine tune the rest of the layers, right? So here, this lock means we have froze these weights, right? Which means we don't touch, we don't fine tune or change the weights for these layers, right? Because the intuition is that these fundamental initial layers, detect those like edges, corners should be similar, right? No matter if this is a natural image or this is a medical image or other type of images. So they will be basically similar. So we don't want to reinvent the wheel, right? So we can keep as is. But on the higher level, right, maybe this medical domain, we need to be, specifically learn something that in particular to this medical image, right? So that's why we need to tune these layers rather just directly adopt the representation that is learned from this natural image. So here we do this network weights update, right, through backpropagation, just specifically into these layers. Okay, so that's the general idea of doing the transfer learning. Okay, see if there's any comments. Okay, can you guys hear me? Because some.
Yes, I can hear.
Okay. Yeah, if you have any issue, like maybe my microphone or maybe the internet connection is not stable, disconnected, let me know. Okay, I may not notice that. Okay. So we just kind of give you the basic idea of doing the transfer learning, right? But in some of the real world applications, right, we may encounter different situations, right? How do we apply transfer learning effectively? So that's the question we want to answer. So here basically is kind of like a few rules of thumb, so you can follow based on the data set at hand. Okay. So let's still using the ImageNet pre-trained model as an example, because that is the most widely used pre-trained model you are probably used in a lot of applications, right? Either you're doing classification or object detection. So ImageNet pre-trained model is the most widely used, pre-trained model. Okay. Now let's consider you have the target set, right? So that's the data set, for your application, either medical image computing or maybe other specific applications. Okay. So there's a couple of situations listed here. So, the first situation or scenario is for your target data set, right? So the data set size is large. Okay. You may have a lot of training examples, fortunately, for your application. But the data set similarity is very different. Okay, so for example, maybe you are doing some medical image, processing, and you have the luxury to collect a lot of labeled data, right? So you have a decent data set size, but the data set is quite different than the ImageNet, right, which is RGB. Okay. So the recommendation, if you want to still do the transfer learning, right, using the pre-trained weights from the ImageNet, is that you can still using the weights from ImageNet pre-trained model, right? We consider this as model A. You can do the initialization using the ImageNet pre-trained weights, and then you can retrain or fine-tune the entire network model from using the data set. Right. So rather you freeze some of the layers. In this case, since you have enough data and also the data is quite different than the ImageNet, you should consider, fine tune the entire network. Okay. But you can using the weights from the pre-trained ImageNet model as the initialization. The second case is still you have a large data set. Okay. But the data set now is very similar. Okay, so maybe we can still using medical image as an example, right? So here we are still, maybe this is not X-ray or MRI or CT, but you still have like RGB, right? Maybe just some users or client taking some of the photos, or maybe like, let's say like a skin disease or classification, right? So still have like RGB type. And the data set bears, very similar, data distribution or characteristics as the pre-trained data set, ImageNet. So in this case, we can maybe just, fine tune a couple of layers, right? So this will less likely to overfit. Okay, so this is the second scenario. The third is the data set is very small, right? Which may be often the case, right? The target set is very small, and also it is very different than the pre-trained data set. Okay, so in this case, we can train a classifier using the earlier layers. Okay, and in other words, the later layers won't help much, right? Because the data set similarity is very different, right? So the later layer, which learns the high level representation, right? So maybe this is not useful for your target domain, but for the earlier layers, as I mentioned, right? So those are some of the fundamentals, so they can still be used here in this case. Okay. And the last case is you have a small data set, and the data set, but is very similar to the pre-trained data set. So in this case, we probably don't need to fine tune some of the layers. So what you can do, or the simplest way you can do, is treating the pre-trained model like the CNN as a feature extractor, right? So you only take the pre-trained model, right? Just directly apply this model on your target data set image. But you don't using the classification layer. You just basically maybe the layer before the fully connected layer, right? So you're just using that as a feature extractor, right? Generate the features using this CNN layer. And then you can, using that feature to train a separate linear classifier, right? The simplest classifier you can do, or you can using other type of classifier like support vector machine, or maybe complex nonlinear classifier. So basically this is, you can treat this pre-trained CNN network as a feature extractor, and just extract the features from the data set, then train a separate, just train a simple separate classifier to do the classification, right? So the intuition is that, data set, bears some similarity, right? So the pre-trained model can be used to extract decent features. And because the data set is small, right, you don't want to do some fine tuning. Maybe there's a risk of overfitting. So in this case, just using the features and train a separate classifier. So this may give you the best performance for your target data set. Okay, of course, this is the general rules of thumb, but in practice, you can always opt for just do fine tuning, right? But here you has to be careful, right? Which layer you're gonna fine tune, right? What kind of learning rate you're gonna specify during the fine tuning, okay? So if you're interested in more in transfer learning, so here are some of the resources, give you some of the step-by-step how you can do the transfer learning, right? Freeze some of the weights from some of the layers and how to specify the learning rate to do the fine tuning, okay? So these are some of the additional material you can read. Okay, and here is I just give an example, right? So in the medical domain, doing the transfer learning. So in this paper, the proposed solution is that instead of transfer the weights for the target application, medical image classification, they're using the scale or the range of the weights, right, instead of the weights themselves. So in this case, they can facilitate the convergence, but may not be adopting the actual weights in their target application. And they also only use the pre-trained weights from the lowest two layers, right? So those are the initial layers. So shares very close similarity, among different data distributions. Okay. And here is an open resource that is specifically designed for transfer learning for 3D medical image analysis. So I think they have pre-trained models specifically for medical image computing, right? So they collect a large amount of medical data to form like ImageNet A-like data set in terms of the scale and the diversity, so that you may have like a medical domain ImageNet, so that you can train a very large model, and this model can be used for transfer learning to some other applications. Okay, so if you're interested, you can check out this GitHub and see if there's anything useful for your application. Okay.